Good morning and welcome for this lecture from Organic Chemistry lecture series. So today we are going to discuss Oppenauer oxidation. So because this is oxidation, now here we can expect addition of the oxygen, loss of hydrogen or loss of electrons. So essentially this oxidation works for secondary alcohols in presence of aluminium tertiary butoxide, that is any metallic alkoxide reagent, and a proton acceptor. They get converted to respective ketones. This reaction is exactly opposite and considered as a reverse of MPV reduction. Because this reaction is carried out in very mild conditions, even sensitive compounds wherein there are a lot of other oxidizable groups, this reaction works well in case of secondary alcohols. This reaction was named after Rupert Oppenauer, who discovered this in 1937. So let's see. Because this reaction takes place in presence of secondary alcohol, first let's compare different types of alcohols. So alcohols are the compounds in which there is a hydroxy group attached to a carbon. Now this carbon, which is bearing hydroxy group, if it is attached to only one alkyl or aryl group, then it is called as primary alcohol. And because valency of the carbon is 4, one bond is utilized with hydroxy group, one bond is with the alkyl group, two other remaining bonds are for hydrogen. Whereas in case of secondary alcohol, the carbon is bonded with two R groups. They can be alkyl or aryl. So there is only one hydrogen. Whereas in tertiary alcohol, carbon is bonded with three alkyl groups or aryl groups. So there is no free hydrogen. So out of this primary, secondary and tertiary alcohol, this Oppenauer oxidation is specific for secondary alcohols. Because this reaction is oxidation, we expect either loss of oxygen, addition of hydrogen or loss of electrons. So this secondary alcohol loses two protons, and to satisfy the valency of carbon as well as oxygen, there is formation of a double bond. That is why this reaction is not applicable to tertiary alcohol. With the said reagents and solvents, reaction is not very specific for primary alcohols, but still it can be carried out. But reaction is most widely used for secondary alcohols. Now to carry out this reaction, we need one metallic reagent which acts as a catalyst. It starts the reaction, increases the speed of reaction. So it is usually a metal and its oxide. So here it is shown isopropyl oxide. There can be tertiary butyl oxide also. Along with this, to carry out this reaction, we need one proton acceptor, which is usually any aldehyde or ketone. So Oppenauer oxidation, though it is possible in primary alcohols also, it is specific for secondary alcohols. For getting oxidized, they lose two hydrogens and form ketone. So in case of primary alcohols, if they are subjected to this reaction, there will be hydrogen, so they will form aldehyde. But this reaction is not much common. It is used for converting secondary alcohols to ketones. Reaction takes place in presence of some metal catalyst and excess of the proton acceptor. There is no strong acid, strong base required for this reaction. So reaction occurs in very mild conditions. Let's discuss mechanism. In the first step, secondary alcohol reacts with aluminum isopropoxide and they form a complex wherein a proton from secondary alcohol is easily transferred to the catalyst and there is a liberation of isopropyl alcohol because we are using isopropoxide. If here we use butoxide, tertiary butyl oxide, then there will be formation of butanol. Now this complex reacts with the excess of ketone which we have taken as a proton acceptor and they form a 6-member transition complex in such a way that carbonyl group of this ketone is in vicinity with our alcohol. So there occurs transfer of the second proton but in the form of hydride, that is H minus. So in the first step there is a reaction between secondary alcohol. Here we have taken, because it is a secondary alcohol, it consists of a carbon which is attached to two alkyl groups. So this lone pair on the oxygen of the alcohol approaches to the metal to form a coordinate bond. There occurs formation of such a complex. Now because oxygen is having 3 bonds, it has to lose 1 bond. So it loses this proton which can easily combine with another oxygen via say quick formation of hydrogen bond and there occurs formation of corresponding alcohol based upon which oxide we have taken in the catalyst. Because we are using excess of ketone, similarly this metal forms a coordinate bond with the oxygen of the ketone. This forms a complex which is 6-membered considering aluminium, 2 oxygens, 2 carbons and a proton. Now there occurs like a sigma-tropic rearrangement, alternate formation and breaking of the bonds. Because this ketone oxygen has formed a bond with aluminium. Now this is in excess, so it tries to break a bond with the carbon. Because carbon is in need of the bond, it can quickly accept the neighboring proton. So the proton gets transferred because it is going to the electron deficient carbon now. It goes as H minus. And this leads to formation of a double bond from the carbon and the oxygen. This is how ketone is released as a product from this metal catalyst. This bulkier complex stabilizes itself by breaking off this ketone as a product. Soon this reaction was discovered. There were lot of modifications which took place. So this Whetstone-Oppenauer oxidation and Oppenauer-Woodward oxidation are two important modifications which were named after the scientists who were involved in these modifications. So Whetstone-Oppenauer oxidation was made applicable to the steroids. So steroids are usually very non-polar and containing 3 or 4 fused rings, and nowadays this reaction is very common for these steroids. So hydroxysteroids were converted to ketosteroids. Proton acceptor they used was benzoquinone. In Oppenauer-Woodward oxidation, this was made applicable to hydroxy compounds which are attached to the aromatic rings. So, and they used potassium tertiary butoxide in place of aluminum alkoxide. So this was made applicable to the alcohols which are difficult to oxidize by the current or conventional method of Oppenauer oxidation. Conversion of quinine to quinone was successfully carried out. Since then, there were several research groups which made use of different metal catalysts. Like some used different forms of aluminum. Instead of alkoxide, they simply used trimethyl, that is alkyl aluminum compound. Then some other research group made use of zirconium, ruthenium, then like Grignard's reagent, some halogenated magnesium oxide, then cyprium, iridium complex, these were used. And proton acceptors, different research groups tried using cyclohexanone, benzophenone, paraformaldehyde, even some aldehydes. Applications. This reaction is nowadays very common for converting saturated as well as unsaturated alcohols such as geraniol, hexanols, nonenols. So all straight chain alcohols can be easily converted into their respective aldehydes or ketones. Very much popular for synthesis of the steroids like cholesterol, which is containing hydroxy group in one of the ring. It can be converted into ketone, and unsaturation is also seen to be shifted in this case. Even in case of non-steroid ketones like decalones, they can also be achieved or synthesized from their corresponding secondary alcohols like decalol. This reaction is very widely used for synthesis of progesterone, which is a female sex hormone, and it finds used as a contraceptive as well as treating various menstrual disorders. So synthesis, like conversion of cholesterol into cholesterol, there occurs conversion of the hydroxyl group into the ketone group, and this unsaturation is also shifted to the ring which is containing ketone. Here they have used cyclohexanone. Then this is one of the steps for synthesis of various analgesics like morphine and codeine. And because we are using conversion of alcohols to the ketones, cyclic ketones as well as cyclic esters like lactones also get formed. So if we have a diol, here we have two hydroxy groups which are in the vicinity, they can cyclize with each other. So out of them, one of the hydroxy group gets converted to a ketone group, and there is reduction in this way. So hydrogen from both the hydroxy groups get removed during this oxidation, and there occurs cyclization. Cyclic ester, C double bond O, and oxygen, these are called as lactones. Also, this reaction has been utilized in the synthesis of terpenoids. These are the natural compounds which are secondary metabolites obtained from the plants. So this is how Oppenauer oxidation is very much useful, and it works at very mild conditions. So substances which are acid labile or not stable in the harsh conditions, they can get easily oxidized. So this is all about the reaction mechanism, modifications and applications of the Oppenauer oxidation. Thank you.